Hi everyone, this is my Physics 2 Lab 3 report. We're going to be observing and measuring how the direction magnitude of magnetic field is dependent on the location of a magnet. In doing this, we'll be taking measurements on axis and off axis and comparing these measurements. The top picture shows how my phone should be oriented for on axis measurements. Bottom picture is how it should be oriented for off axis measurements. I'll also be using and applying the Biot-Savart law and distance dependence formula in order to find an experimental mu value. Some assumptions I made were that I could neglect the effect of Earth's magnetic field as long as I compensate for it, and that other objects aren't interfering with the field. And I assumed this because I was compensating for other objects by performing my experiment outdoors where no electronics were present other than my laptop to write down and write down my calculations. Some predictions I made were that the on-axis fields should point in the same direction and the off-axis fields would point in the opposite direction of on-axis. I also found that n equaled negative 5.21 and mu equals 1.31 times 10 to the 1. In my data tables, in the top left corner, you can see my recorded results for my on-axis fields, and my bottom chart shows my data for my off-axis field. And then you can also see the calculations for what the values for my 45-degree angle should be. So I got for the x component 10.23, y component 70.7, z component negative 44.1. These values are quite large, so there may have been some sort of issue with how I compensated for magnetic north or some issue somewhere with my unit conversions. And then with this data, I was able to plot a line for ln of b versus ln of r, which gave me an equation y equals mx plus b. And using the y-intercept and slope, I'm able to find the value for n and the value for k. And then by doing some algebra, I'm able to find my experimental mu value per the equation for k, which is equals mu naught over 4 pi times 2 mu. For my code, I use this experimental mu value in order to calculate the magnitudes and directions of the magnetic fields at different locations. So line 24 is my experimental mu value that I got, and then I created a function to calculate the magnetic field of a dipole. I used kind of the same idea from Lab 0, but applied the idea of electric field to magnetic field. And then the highlighted areas show what I defined for my position vector and what I was defining for my function for magnetic field of a dipole. And then for D, for my magnetic field of a 45-degree angle, I use cosine 45 for the x component, sine 45 for the y component, and multiply both of these by d perp in order to get the x and y components for the vector form that I needed. And then for my magnetic field at 45-degree angle, again, I applied my function for the B field of a dipole. And then you can see the arrows from my code. Orange equals on axis, cyan is off axis or perpendicular, green is my 45-degree angle. And then you can see in my code that I calculated that B at the 45-degree angle at distance d should equal what appears to be a smaller number than what I got from my experimental data in my Excel sheet, which again implies that there was some sort of issue with probably compensating for the magnetic north or with unit conversions. In conclusion, as the distance between magnet and magnetometer decreases, the magnetic field increases, which makes sense because of the 1 over Rn component of the magnetic field of a dipole. And if I hadn't compensated for magnetic north, then I would be accounting for other values that that aren't just from the magnet, but from other objects such as electronics or the Earth. And two bar magnets stuck together allows me to use the superposition principle. So I'm adding up both of the magnetic fields from both bar magnets, which then creates approximately a twice as strong magnetic field when these magnets are stuck together.